Now I'm delighted to introduce our speaker and my friend, Randy Davila. Randy's a mathematician and AI researcher working at the intersection of graph theory, combinatorics, and AI-driven mathematical discovery. He serves as our own member of technical staff here at First Principles and as a lecturer in computational applied mathematics and operations research at Rice University. He earned his PhD in mathematics from the University of Johannesburg in 2019. His work includes contributions to zero forcing, domination, and combinatorial optimization, as well as recent research on automated conjecturing, counterexample generation, theory revision, and machine learning systems for mathematical reasoning. He has delivered invited talks at institutions and conferences, including Harvard University, the California Institute of Technology, Rice University, and the Joint Mathematics meetings, as well as our house mathematics and AI workshop very recently. Please welcome me in giving Randy a warm welcome. And Randy, without any more discussion, I will pass it over to you.
Okay, thank you for that warm introduction, and I'm happy to be giving a talk here internally. So this talk is all about the discovery aspect of mathematics using AI. Automated conjecturing is what I call it. Internal theories are the things that I believe that such systems build, and generally this just falls under the umbrella of AI discovery. So, okay, how does discovery work for a mathematician? Well, typically you'll sit around with coffee or at a bar with some friends and fellow mathematicians, investigate some given topic, and conjecture wildly at first, right? This is how things start. But after you have these wild conjectures, that most of them are false, you investigate, and these investigations lead to counterexamples, most likely at the very beginning. Extremal structures that you need to construct in order to break the wild conjectures that you said prior. Occasionally, you'll find a simple proof, and then maybe this isn't deep enough for a research paper, and you conjecture wildly again, and you update your experience based off of either the proofs or the counterexamples that you generate with your friends, and then you conjecture again, investigate, search for counterexamples or proof, and just repeat this process over and over again. Well, this is the life of a mathematician. It's to prove and to conjecture, as Paul Erdős would say. On the proving side, proof search is driven by small lemmas, or sometimes deep informative lemmas, inventing new definitions, previous intuition, and referencing previous results. And verification is typically done by expert refereeing, and now with formalization systems like Lean4. On the conjecturing side, though, conjecture search is driven by examples, concrete examples that you are able to write out and investigate. You compute, you use some intuition, you try to generalize and have the strongest statements that you can, and selection is based off of quote unquote interestingness or aesthetics and impact. Does the statement you're investigating actually mean something to the mathematical community? Well, many of the parts of conjecturing here, though, examples, which is data, computation, these can be modeled with the computer. You can, that's precisely what computers are made for. Now, but the intuition, the strength and the generalization is something a little bit different, which we can impose with heuristics, as we'll see. Okay, so what does it mean to be a good conjecture? So this talk is going to focus on the conjecturing aspect of discovery. So what does it mean to be a good conjecture? Well, I would argue that a good conjecture is not dependent on its truth value. In fact, my good friend, Dr. Ryan Pepper at the University of Houston downtown recently said to me that some of his favorite conjectures are the ones that were false, the difficult false ones, the ones that you have to think very deeply about and construct elaborate examples to break them. So false conjectures can indeed lead to new research, interesting counterexamples, and new theory. That's a driving point that I want to make clear throughout this talk, is that the goal of a conjecture is not out of sample generalization like machine learning is. The conjectures should they should be strong, but it doesn't matter if they're true or false. What matters is that they drive mathematical investigation. What's more, some mathematical statements may indeed be undecidable, neither provably true or false, but are surely still important to the scientific progress. For example, the Riemann hypothesis, or even Goldbach's conjecture, and so on. We may never know if these are true or false statements, yet they still drive many aspects of mathematical research. What's more, many true conjectures are trivial and don't stimulate anything. They're just kind of consequences of the definitions. So good conjectures should stimulate research. They shouldn't necessarily be true. So why would we conjecture? Well, again, so the primary use case here is not out of sample generalization, but rather as a tool for theory expansion. So when I collect a collection of conjectures on a given topic, that is my internal theory based off of my experience. My experience is derived from data. And these conjectures, these internal theories, batches of them, are what motivate the exploration. We must search for the boundaries of this internal theory. What might we be missing in our data that would correct our internal theory if we added it to the known set of data? Okay, so is AI conjecturing hard? Like, can machines conjecture like humans can? Well, there are some quotes here from well-known famous people. For example, Demis Hassabis of DeepMind, quoted here to say, to solve a famous conjecture that's within reach now, but they won't be able to come up with the conjectures. Here, Terence Tao was quoted in saying that we do not have the mechanisms of posing open problems and formulating conjectures which work well enough, but we don't really have a culture of throwing out less precise but still informed speculation on where a subject might be headed. That, to me, is such an insightful quote, because in machine learning, in machine learning culture, correctness is the guiding principle, whereas I kind of think, no, maybe we need to speculate more and throw out less precise statements. So let's talk about AI conjecturing and give a brief history here. So the notion of computers generating conjectures dates all the way back to the 50s with Wang's program 2, and there's been dozens, or well, maybe not dozens, a handful of notable systems since the 50s, such as Linux AM, which is short for Automated Mathematician, Epstein's GT, which is the graph theorist system, Philo-which's Graffiti, Delavigna's Graffiti.pc, Hansen and Comprosi's AGX, Larson's Conjecturing, Merlot's Graphedron, and its extension Fogue, and then my system's TxGraffiti and Graffiti3. And we're going to focus on only a few of these for the sake of time. Wang's program, Philo-which's Graffiti, Merlot's Graphedron, and TxGraffiti to now Graffiti3. So Wang's program 2 was developed at Bell Laboratories in the late 50s and is widely viewed as the first automated conjecture machine. Notably, Wang's program 1 was one of the first automated theorem provers. So he had two insights here that AI may one day help with the mathematical discovery loop. And the way the system worked, it explored propositional logic formulas. It mined data and very quickly generated 14,000 well-informed formulas in just a few hours. When I say well-informed, I mean that on the data that he was using, these 14,000 statements, or roughly 14,000 statements, were true. They weren't proven to be true, but they were true on the data. They were suggestive of things to study. However, most of the statements were trivial or uninteresting, highlighting a combinatorial explosion problem, which I call the fundamental problem of automated conjecturing, that a computer can systematically check various arithmetic expressions, logical operations applied to predicates, and enumerate a vast amount of statements quickly. Of these, though, which of them are important? Which of them are interesting? And that is the focus of automated conjecturing. That is the fundamental problem, how to filter down to the meat, the informative internal theories of the system. And the first program to overcome this, I would argue, is Feitlowich's Graffiti program, named Graffiti because the conjectures of the program were metaphorically spray painted, written on the wall for mathematicians to investigate. And the way, the key insight that Feitlowich had with Graffiti were to introduce heuristics to filter out the noise that a computer may overly generate. And specifically, the most well-known of his heuristics was the Dalmatian heuristic, developed in conjunction with his PhD student, Ermelinda Della Vigna. And this Dalmatian heuristic consisted of two tests. One, so the first was the truth test. So a newly found conjecture must hold for all of the known data. Well, that one seems clear to me, that you want a given statement to be true on all known examples. And then the second test was the significance test. The new conjecture must improve on all prior computer conjectures for at least one example. So I should probably state now that Graffiti primarily made conjectures in the form of inequalities. Propositional statements, if P then Q, where Q was an inequality on a given mathematical function, or more specifically, on a graph invariant or a chemical graph invariant. For example, you see this theorem here, proven by Fan Chung. This is one of the earliest results, discoveries that was stimulated by a computer-generated conjecture that says that if you have a simple graph with average distance d, av, then the independence number is bounded below by the average distance. This was a very surprising result, that that this lower bound, the sharp lower bound, was true, and it was completely inspired by the program Graffiti. And to emphasize the impact that Graffiti had on the discrete mathematics community, at least 60, but likely over 100 conjectures from Graffiti have been proven and published in respectable journals, such as the Journal of Graph Theory, where I think this theorem of Chung appeared. So computers can indeed influence mathematical literature. They can find new things to work on. Now, back to the significance test here, what does it mean to improve on all prior conjectures? Well, if you look at this bound on the independence number below, alpha greater than or equal to d average, that bound was presented by the system because it is sharp on at least one instance, one graph instance, where no other bounds are sharp. So it improves on the internal theory of conjectures for at least one graph. If it didn't, then it would have never appeared, according to the Dalmatian heuristic. Okay. So heuristics are going to be important going forward. The next notable system is Melot's graphedron. It's a play on polyhedron, the naming, I mean. And this one I think is important because of the geometric interpretation of what it means to conjecture. So if you have a collection of mathematical objects, in this case graphs, you can annotate each of them with an invariant vector. So for example, the number of vertices, the average distance, the diameter, the independence number. So each mathematical object can be annotated with a vector of invariance, which then places them in space. And once you have a collection of objects, so for example, this little image here, there's 5 mathematical objects. They form a point cloud in space, and then you can compute the convex hull of those points with those given invariants, F1 and F2 in this case. And the facets of this whole can be interpreted as inequalities bounding one invariant by another in 2 dimensions here. But if you had 3 dimensions, then you would have linear, fine inequalities relating the invariants. So, and what's more is that if you compute the convex whole, then you know that these facets are like the extreme bounding inequalities relating these invariants. I don't have time to go into it, but there is an extension of this Graphitron called FOG, which looks at the vertices as extremal values for which then you can search for counterexamples. And this is something that the program AGX definitely worked with this algorithm called variable neighborhood search, where you look at extremals and you tweak the structure of the objects just a little bit to try to nudge out of that point cloud so that you break one of the conjectures that you're looking at. And this indeed actually did lead to counterexamples to many of the not many, but several of the conjectures of the graffiti program. So these systems fall under the umbrella of what I would call automated conjecturing. So what exactly is automated conjecturing? So this is, well, a specialized subfield of artificial intelligence concerned with the design and analysis of computer systems that propose novel mathematical conjectures, or attempt to propose novel mathematical conjectures. And the way that my systems tend to work is with these bullet points here is that we start with a snapshot of mathematical instances. So you have maybe 100,000 integers, or you have 300 graphs, or whatever objects you're studying. This is a snapshot of data that's going to inform the possible conjectures that you can make. And then you mine for conditional and biconditional statements on this snapshot of data. You filter and generalize with heuristics according to strength. Is the inequality tight? Is the statement as general as possible? Apply the Dalmatian heuristic, so forth and so on. And you return a small collection of human-readable snapshot true symbolic statements for a human or for an AI to investigate. Now, again, to emphasize this point, automated conjecturing is not machine learning. And the fundamental difference is as follows. In automated conjecturing, the goal is not out-of-sample generalization. Machine learning is defined by it. Automated conjecturing uses all available data when making conjectures. In machine learning, train and test splits are fundamental. The reason I believe that automated conjecturing should use all available data is the extremal values that are there. You want to add interesting data to your current snapshot, so you need the strongest possible statements that you can make. You have to use all of the data to find those strong statements. Even if they turn out to be false, you will update your data if they are false. Okay, so mathematical snapshots, just to be clear, we take objects and we annotate them with a vector of real and Boolean value descriptors. Each instance becomes a vector of information. Sets of instances become a point cloud in space. A snapshot is the invariant cloud of all currently known examples. And these snapshots are the on-disk memory of an automated conjecturing program. Now, let me share a different screen now and show you what an old version of this program looks like. So here, you'll see my old TxGraffiti Streamlit app. So TxGraffiti is short for Texas Graffiti. This was a system that I've developed over the past decade now, 10 years ago. And around 2021 or so, I decided to make an app for my colleagues to use instead of me sending them conjectures of the program in graph theory. And this program works on a snapshot of about 350 or so graphs that were curated over time through conjecturing, finding counterexamples, adding them to the data, conjecturing again, finding more counterexamples, adding them to the data, repeating over and over again. So you can think of this as online learning. snapshots are precisely that, snapshots. They're meant to be updated with time, and that's how the systems become better. So suppose we want to conjecture on something like the independence number. We can select maybe connected graphs, just keep things simple. We can look at computable bounds, and then we can mine that snapshot of data for inequalities, in this case, linear ones. I keep it simple, or I kept it simple for the app to restrict to just fine bounds. So here we see that the top conjecture after the mining process and heuristics and sorting are applied, that we see that it looks like the independence number is bounded above by half of the energy of the line graph. Whatever, that's the sum of absolute values of the adjacency matrix of the line graph. That's a kind of weird looking thing. It's non-linear, but it is in a fine bound if you treat that as a single scalar. And we see a nice plot here showing that this is kind of reasonable. What's the next one? That's a weird looking one. So this says that the independence number is bounded above by some sum. Oh, I know this one, of the 2 degree multiplied square root of blah, 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 whatever, but it's a bound on the independence number that a human probably would have never come up with. What's more interesting about this one, there's 2 things. How did this sum come from? Well, back when I was writing this online program, or this system, it wasn't too much longer after that GPT first came out. And I asked GPT to come up with interesting degree sequence invariant types of things to inject into my snapshot table to conjecture on. And one of them happened to be the reciprocal of this geometric arithmetic index. And then it said the 2 degree instead of the 1 degree. So the 2 degree is like a generalization of the 1 degree. So this appeared as soon as that LLM suggested for me to include that as a value in the snapshot table to conjecture on. And again, a human would probably never come up with this. Recently, though, I was teaching graph theory, and we were investigating some of the conjectures of the program. We found a counterexample to this, but the counterexample to this, the smallest one that we could find, was on 16,000 or so vertices. So the plot here would indicate maybe this might be true, but it actually does break for these things called spider graphs when there's 16,000 pendants on the thing, which was surprising to me. But again, that's the whole point of automated conjecturing, is that you find these really weird extremal structures that merit investigation. What's more, you also derive a new problem. So we found a counterexample on 16,000. The new problem is, what is the smallest order graph that breaks this conjecture? That's a new problem to work on, and actually something that would probably result in a theorem saying the smallest value that would break this is on the order of like maybe 10,000 or something. I don't know. But again, that's interesting. It's stimulating. Also, if that were to be the case, then this has real application meaning, because the independence number is NP hard to compute. This is a sharp bound. If everything below 10,000 vertices satisfies this bound, then we have an application that we can use in real life. Okay, so let me go back to my slides. Okay. Okay, so let's go back to the basics of how my systems work. So suppose we have 3 mathematical objects, in this case, the 3 smallest non-trivial connected graphs. We annotate them with Boolean and numeric invariants. So for example, the number of vertices, the number of edges, the radius, and then the predicate, is it a tree? So we have this snapshot table. And then from this table, we can mine for conjectures. For example, these 4 conjectures, which I would consider an internal theory. Number of vertices and most number of edges. If it's a tree, number of vertices equals number of edges plus 1. If it's connected, the radius is equal to 1. But then once we have this internal theory, we should investigate which of these are, surely some of them are false, and indeed that one would be false. And this graph here, G4, is a counterexample to that statement. So we add that to our data, we update our snapshot, and then we repeat. And this process of going, of adding counterexamples, updating the snapshot table, conjecturing again, within a few iterations in practice, you'll find that you'll either get to a place where the conjectures are very difficult to break and they're false, but they're still very difficult to break, or you end up finding true theorems. Okay. So what does this look like in practice? Well, I call this the optimist and the pessimist, where the optimist is the system that conjectures, the pessimist is the one that fights them. Okay. But for the sake of time, I'm going to move to the new system, which I call Graffiti3. So Graffiti3 is the culmination of the past 10 years of working on conjecturing progress with Texas Graffiti, and then also adding in snippets of ideas from all of the previous systems, including Graffiti, Graffiti.pc, Graphtron, not AGX yet, but I'll get there eventually, and also Conjecturing. Okay, so Graffiti3 it's more of an algorithm than a system. It's a pipeline that turns snapshot invariant tables into these internal theories of quantitative and structural conjectures. And the stages are as follows. So we have a table of numeric and Boolean values. That's the snapshot. The pipeline automatically assembles a hypothesis poset from the available Boolean columns. And then the user selects a target numerical column or columns to conjecture on. The system then solves sequential optimization problems over the combinations of the remaining numerical columns to find tight inequalities on the targets. And thereafter ranks and filters the resulting set, which are necessary conditions on these target numerical values. And then from those necessary conditions, we can introduce sufficient conditions using now mixed integer programming to mine for if inequality, then Boolean predicate, and then filter with a property version of Dalmatian. Okay, so how does well, we need to build up some notation first before getting into that meat. So suppose we have n objects. So these can be graphs, integers, matrices, whatever. So n objects together with invariants computed on those objects and predicates computed on those objects, which gives us our snapshot table. We write numerical columns with I and the predicates with P. And the first stage is to build this hypothesis poset. So when the system looks at the table, it looks and checks if there's any predicates that are true on all rows in each of the rows of the object. So if it finds any predicate that's true on all rows, it flags those as a part of the base hypothesis, and then it takes the conjunction over those as the base. It's like, what objects are we looking at? For graphs, in my data set, it would see, oh, the connected column is always true, the non-trivial column is always true, so the base hypothesis would be connected and non-trivial. That sets the stage for the rest of the possible hypothesis to check. So once you have your base hypothesis, which are the conjunction of predicates that are true on all rows, then you can mine for interesting other hypotheses. So for example, B and predicate R1 would be connected and non-trivial, that's the base, and bipartite, connected and non-trivial, and cubic or regular, things like this. And there is a filtering process that goes into this so that we don't get redundant hypothesis. So we won't get something like connected and non-trivial and cubic and regular would be redundant, because if we drop regular, the support defined here wouldn't change. So there are filtering processes to get only the hypotheses that are meaningful. And once you have a set of hypotheses, then we can choose a numerical target, this I star thing, which is just a mapping from the objects to the reals, and generate a large collection of snapshot true statements of the form for all objects O. If the hypothesis is true, then the invariant is bounded by some function of the other invariant, such that I not star thing is. And the little cross there can be either less than or equal to, greater than or equal to, or equal. And these inequalities and equations are found, again, just using simple linear programming with a slack variable so that we minimize the distance from one side to the other, making it as sharp as bounds as possible. So for example, we would have here at the bottom, if H, then I is at most weight 1, which is found by the linear optimization, times IA, so that's another invariant, plus weight 2, that's again found by the linear optimization, times the square root of this product plus the intercept B. So W's and B's are found with linear optimization. The other, the product there and the square root are found through just a combinatorial, like enumeration of the possible candidates or grammar that we can use. Okay, so once we mine these inequalities and equations, these these necessary conditions, or these necessary bounds on the target, we then will filter with heuristics. So there's 3 main heuristics here. The Morgan heuristic says generalize the hypothesis when possible. So for example, if you have, if tree, then some inequality, the system will check if it can lift the hypothesis to a more general hypothesis, one that is true on more rows. So it would try to lift it to bipartite, and then it would try to lift it to just connected and non-trivial until the statement is no longer true, and it keeps the most general hypothesis. So the statements are as general as can be. Then we use a Dalmatian style heuristic to remove conjectures that are not informative with respect to the others. And then we order them with this Hazel ordering that says that we count the number of times that an inequality might be equal. That's its touch number. And then we sort by that number and remove ones that don't touch at all. So I think this is a good point to maybe describe the details of the Dalmatian-like heuristic. So suppose we have 3 objects here with real value descriptors alpha, beta, and n and chi, and we get 3 conjectures. So suppose the system finds 3 conjectures, 3 conjectured upper bounds on alpha. So we can then, once we have these inequalities, investigate how close the inequalities are. So for conjecture 1, that it's strict on the first 2 objects, but tight on the 3rd object. So tight on 3rd object, strict on the first 2. For conjecture 2, we can see that it's strict on object 1 and object 3, but tight on object 2. Okay. And then for conjecture 3, we can see that it's tight on object 1 and 3, but the inequality is loose on object 2. So this tightest known bound, I'm going to say, okay, that goes to the front. So the tight bound is informative at object 1 and 3 because it's tight there. So conjecture 3 is the best one so far. But which of the other 2 should we add? Well, let's investigate the informativeness of conjecture 1. So object 3 is already covered by conjecture 3. So conjecture 1 might not be informative, but if you look at the blue squares there, object 2 is accounted for by conjecture 2. So if I were to have to choose between C1 and C2 to add to my list, which one do you think that I would choose? I would choose C2 because that is informative relative to conjecture 3. So then I would keep C3 and C2 and get rid of C1. Then there's an added benefit here that we can combine these conjectures and take the minimum of them, of the upper bounds, to get an equality. So this is a side effect of having these informative bounds included in your set. okay? But once we have these inequalities, C3 and C2, these now become predicates, right? Like, so you can make them strict and equal and you get predicates. So here we see that C1, Sophie, I call it, inspired by Delavigne's Sophie heuristic, alpha strictly less than beta, and then C2, alpha equals to beta. So these are now predicates, and we can say, okay, do these predicates imply any other predicates in the data? So here I'm just making up predicates. H odd is one predicate where if the index is odd, and H even is the predicate if the index is even. So then we can see alpha strictly less than beta implies H even, right? And then we can say, okay, if they equal, that implies H odd. In fact, we get biconditionals. So by treating the conclusions of the necessary statements, the inequalities, as predicates, we can then mine for if inequality, then predicate, and search for those. And then when we get equal support on the left and right hand sides, we get a biconditional statement. So it's important to note here that LLMs assist in this process. As I mentioned when I pulled up the TxGraffiti app, that the LLM injected into my snapshot table that weird sum of the 2 degrees, which then led to an interesting conjecture to stimulate research. So it was apparent to me from the outset of GPT coming out that there is a way of interacting with a classic automated conjecturing system like mine with an LLM, which motivates this this pipeline of an LLM to propose the invariants and properties of the study. I take that, I run that code, which creates a snapshot table. I give that to the Graffiti3 system, which the Graffiti3 system then conjectures on that table. I provide those conjectures to the LLM, and then the LLM critiques, finds counterexamples, gives me the updated code to update the table. I feed this back to Graffiti3, which conjectures again, and I give this back to the LLM, and this cycle repeats. And this cycle was useful for me over the past year, as I've been giving talks all over the place about automated conjecturing. And inevitably, at the end of each talk, someone would ask me, hey, can you conjecture on my data? And it was often in fields that I'm not familiar with. So I needed a way of producing conjectures for areas that I wasn't an expert with. And this was the feedback loop that I came up with. And to illustrate this, I asked several months ago now, GPT to produce, I wanted to study integer data, close enough to graph theory where I could, well, I'm a mathematician, I can understand most of the definitions, but I didn't know what to study. And GPT suggested the following descriptors: the Euler-Totient, the Carmichael function, the radical, the count of prime factors, with and without multiplicity, the divisor counting function, the divisor sum function. I wouldn't have thought to make those up. It just said these should be interesting. And then it gave me some predicates: is prime, is square free, which I'd never heard of before. Square free, it's a simple definition. If the prime factorization doesn't have any powers greater than 2 or greater, then it's square free. A definition called is almost square free, which it made up. If it's perfect, if it's a prime square, is it 7 smooth? So these are all things that the LLM proposed for the snapshot table. And then the LLM gave me code to produce a table of all of these values computed on integers up to, I forget what number, but it was a good table to work with. I gave that table to Graffiti3, and then I asked the LLM what to conjecture on, and it suggested to conjecture on the Euler-Totient. And immediately, these conjectures popped out. So the Euler-Totient is at least the Carmichael. Euler-Totient is at most n-1. Euler-Totient equals n-1 if and only if prime. And then these weird square root product things, these conjectures. But again, in the triage phase of the LLM cycle that I presented, it flagged the top 3 as known. I went and checked. By definition, they're essentially easy to see. But the other ones it flagged as interesting. And there's actually more than this. So I have a whole document saving all of them, but these are the top interesting ones that the LLM suggested. And turns out that 4 of them we were able to prove. And then the last one is related to, in fact, if that conjecture is true, then there must exist an odd perfect number, which is, there's a big open problem if odd perfect numbers exist. So it's related to something that people really think about. So I'll focus on one of them, this theorem now. If n is square free, so n is square free if and only if that inequality is satisfied. Moreover, this inequality holds with equality if and only if n is prime. So in the investigation of this, I asked GPT like why it thought this one was interesting, and it produced code for me to plot the square free versus non-square free integer values, like taking the Euler-Totient minus the right-hand side, that's like this boundary, or the right-hand side minus the Euler-Totient. And that's what this plot is, up to 10 to the power almost 7. And you can see clearly that the square free integers lie on one side of the line, non-square free integers lie below it, and the integers on that line are precisely the prime numbers. I happened to be on the phone with my friend Dan Romick, who is well known for solving this couch or sofa problem. When I was working with GPT on this problem, and I mentioned it to him, and then later that night he sent me a proof of the first part of the statement, and then I was able to finish off the if and only if n is prime part of the statement, which was pretty interesting. It's a clean, very interesting looking plot that characterizes square free integers. But that wasn't the only one. There were several of these statements that I worked with GPT and to find and help prove things on the statements of Graffiti3. So for example, this other square free characterization that n is not square free if and only if Euler-Totient is at most n minus the radical. Moreover, this inequality holds with equality if and only if n is p squared for some prime number p. There was another one here, another one here. But again, this pipeline was really interesting to see, because I'd never worked with these integer like definitions before, and the discovery process was very quick. To have the LLM produce a snapshot table, me to pass that to Graffiti3, which then made conjectures, which I gave to the LLM for triage, investigate them, look at citations, get help, update the data with a counterexample, conjecture again, repeat, and then produce these papers. And then also, we can skip over this, but there was an investigation by the LLM about why this open problem is interesting and related to odd perfect numbers. Oh no, it says that if that conjecture is true, then no odd perfect number exists. That's what that says. Okay, and there is a paper associated with this, so I can open that up just to show you. I have to share my screen again.
Randy, so should we ask the audience for any questions while you're digging this up?
Yeah. Is the screen flickering on your side?
No, it's stable, and we see the George Pulia.
Oh yeah, to be a good mathematician or good gambler or good at anything, you must be a good guesser. I love that quote. But yeah, we can take questions, but I just wanted to scroll down real fast and show you that. So TxGraffiti and thus Graffiti3 has led to numerous publications in graph theory, but this pipeline here applied to integer data I just talked about, but I went on to also apply this to group theory. So there's like finite groups. You can conjecture there and get interesting things as well. You can conjecture on knots, and you can conjecture on Calabi threefold hypersurfaces. The list goes on. This loop of LLM to Graffiti3 and back is the real interesting part of this study. And I'll go ahead and stop there because it's 10:50.